Hello, everybody. Good morning, good afternoon, and good evening to one and all. I'm saying good morning because our speaker today is uh, in the early morning, wherever in the time zone is. I welcome you all to this webinar, which is on the topic of load testing of bridges, current international practices. My name is Alok Bhaumik, and I'm the Chairman, Professional Development and Technical Events Committee of Indian Association of Structural Engineers. The topic of the day is extremely relevant for the structural engineers who are involved in bridge design and construction. It's a topic which is internationally of interest. Historically, the load testing used to be performed invariably prior to the opening of any bridge to show the traveling public that the bridge is safe. I read many papers where it is mentioned that in the olden days, the designer is supposed to stand on the bridge or under the bridge during the load testing to prove his credibility to the society at large. Of course, today scenario is different. The engineer is not supposed to stand at the time of load testing. But in today's scenario, there can be several reasons which necessitates load testing of bridge superstructure. It can be performed as a part of a validation before the bridge is open to traffic. It can be performed to rate a bridge, and it can also be performed after carrying out the required repair works to validate the retrofitting measures or rehabilitation measures. Sometimes load testing of decommissioned bridges are also performed by researchers to study the true capacity of or the level of conservatism in the design, which helps them to sort of calculate or to decide on the policies on the code making and the margin of safety. We have been realizing for a long, because we in India, we have two codes for load testing. One is IRC SP 51, those who are conversant with Indian highway codes. We have one IRC SP 51, which is for load testing of new bridges, proof load testing. And we also have IRC SP 37, which is for assessment, which is essentially for the testing of existing bridges or rating of bridges. And therefore, we have been realizing for a long that we need to have a discussion, and we need to know what is the international practice. We should bring it in the forum, and therefore that is the background for planning this webinar. And we are very fortunate to have with us today a very eminent speaker, Dr. Eva Landsort, who will enlighten us by sharing her knowledge and wisdom on the subject. We also have today two very eminent panelists with us who will share their views and thoughts on the subject after the presentation by Dr. Landsort. We have Mr. Amitabh Ghoshal, who I think hardly requires any introduction to this fraternity. He's one of the pillars of strength for the structural engineering fraternity. And we also have with us Mr. R.K. Jayagopal, a very well-known personality who has extensive knowledge and has performed more than 100 load testing of bridges in his career. Before I hand over the floor to the speaker of the day, that is Dr. Landsort, I have the proud privilege to introduce her. Dr. Landsort graduated with a master's degree in civil engineering from the Witwatersrand University of Brussels, that is in Belgium, in 2008. She later earned a master's degree in structural engineering at the Georgia Institute of Technology in USA in 2009. She earned the title of Doctor in Structural Engineering from the Delft University, Netherlands in 2013. In the academic field, Dr. Landsort is a full professor at the University San Francisco de Quito, that is in Ecuador, and a tenured assistant professor at the Delft University, Netherlands. The industry experience of Dr. Landsort includes design work in structural and bridge engineering in Belgium, and working as an independent consultant in structural engineering in Ecuador. Dr. Lansot is an active member of technical committees of the Transportation Research Board in Concrete Bridges, that is AKB 30, and the Secretary of Testing and Evaluation of Transportation Structures, that is AKB 40. She is a member of the Technical Committee of American Concrete Institute and the German, there is institutions, that is DAFSTB 445D. She is incoming secretary of the joint ACI ASC Committee on the Design of Reinforced Concrete Slabs, that is ACI ASC 421. She is vice chair of the Committee on Torsion and a member of the ACI Committees on Evaluation of Concrete Bridges and Concrete Bridge Elements, that is ACI 342, and also on shear and torsion, that is ACI ASC 445. She is also an associate member of the Committee on Strength Evaluation of Existing Concrete Structure, that is ACI 437. Her field of research is the design and analysis of concrete structures and analysis of existing bridges. It can be seen, friends, that though she is very young, if you go by her years of experience, but her deep knowledge, her accomplishment in such a short career span puts her in a very high pedestal. Without further ado, I would now like to hand over the floor to Dr. Eva Lansot for making her presentation. Over to you, Dr. Lansot.
Thank you very much for the kind introduction. I will proceed with sharing my screen to start the presentation. So you should be able to see my screen at the moment. And the topic of today's presentation is load testing of bridges. And I have divided today's presentation into the following topics. I'm going to first start with a definition of load testing, then the types and classification of load tests, the feasibility of load testing, which especially in assessment situations is always important to think before you do. And so I will discuss the feasibility of load testing. Then some general considerations in terms of preparation, execution, and analysis of load tests. Mr. Boemink already mentioned that there are different practices for load testing of new bridges as compared to existing bridges. So I will discuss that. Then I will get into the international use of bridge load testing and current developments in that respect. And then I'll round off with some insights from the research that we are currently doing on this topic of bridge load testing. So let's start with the definition of load testing. The definition that I took is the definition from the AASHTO Manual for Bridge Evaluation. And although it's a full paragraph, I do think it's important to take a moment and go through this text with you, as it contains all the basic and important elements of what load testing is. So in the AASHTO Manual for Bridge Evaluation of 2016, load testing is defined as follows. It says load testing is the observation and measurement of the response of a bridge subjected to controlled and predetermined loadings without causing changes in the elastic response of the structures. Load tests can be used to verify both component and system performance under a known live load and provide an alternative evaluation methodology to analytically computing the load rating of a bridge. Now, since this is a definition from a bridge evaluation code or manual, it is related to load testing of existing bridges. But let's look at the details of this definition, because these are essential elements, necessary elements for a load test. And if we look at that definition, we see that what we need for a load test is the following. We need measurements. So we will need to think about the sensors that we apply. We have what they call controlled and predetermined loading, which means that we need to think about the magnitude of that load and how we apply that load. And we're not allowed to cause damage to the bridge, which especially when it comes to proof load testing, which involves higher loads, means that we need to talk about stop criteria. In other words, thresholds to the structural responses that indicate that further loading would cause damage to the bridge. That's, of course, then related to the sensors. And in order to bring sensors to the stop criteria, or the output of the sensors, we really need to have a good understanding of structural behavior. Now, with that said, let's have a look at the types and classification of load tests. Now, the type of load tests that I have contrasted here, being diagnostic and proof load tests, is generally static load tests. I'm not going to talk about dynamic testing of bridges here. I'm just going to talk about typical applications of load testing, which is diagnostic load testing and proof load testing generally. And as you can see here, here's a photograph of diagnostic load test, and you see it's with trucks that are applied and a certain way in which the trucks drive to apply the loads, a known load on the bridge, and generate a certain structural response. Then when it comes to proof load testing, the idea of a proof load test is that we apply a load that is representative of the factored live load that the bridge needs to be able to carry according to the code. And then by applying that load, we show or demonstrate directly with the test that the bridge fulfills the code requirements. And here you see an application where that large amount of load is applied actually with dead weights. You see that it's all piled on the bridge, which can be very risky, as if damage occurs to the bridge, it's not possible to immediately remove the loading from the bridge. The examples that you see here, the diagnostic load test is an application from the United States, but in the state of Delaware. And this application of proof load testing here is from the Barcza Bridge in Poland. Now, what are some general characteristics of these type of load tests? First up, a diagnostic load test, and especially in the application for existing structures, is that we use it to calibrate an analytical model, and in many cases, a finite element model. In one of the documents that we developed with our working group in TRB, we called it developing a field verified model of the structure. So we use the responses measured in the field to improve the models that we are using for rating the bridge. One of the things that we can do, for example, is measure strains over the girder height, which would give us an idea of the position of the neutral axis, and thus can give us information about the amount of cracking, as well as whether we have composite action or not. These types of tests can be done with low load levels. Essentially, the load has to be large enough to generate a relevant structural response. And depending on the codes that we look at, these load levels tend to be recommended to be around 60 to 70% of the live load that is used by the code. We can also use a diagnostic load test as a confirmation of behavior after the design of a new bridge. And as I mentioned before, we are going to use the field test results to update the analytical model that we have, and then adjust that model for load rating of the bridge. Then for a proof load test, as I mentioned before, that's a type of test that demonstrates that the bridge fulfills the code requirements. Now, the loads that are involved typically are representative of the factored live loads of the code. So that means that we're dealing with very large loads, and the higher the load we apply on the bridge, of course, the higher risk is involved. So for this case, our measurements become critical to capture any nonlinearity or any sign of damage to the bridge that can be emitted. And then also these stop criteria become very important. So for both diagnostic load testing and proof load testing, the measurements are important, but for different reasons. Now, if you look at load testing for load rating, if you look at the rating factor as used in the AASHTO manual for bridge evaluation, we see that it is defined as the rating factor is the capacity minus the factored dead load effect minus the factored superimposed dead load effect plus minus, depending on whether it's positive or negative, the factored pre-stressing effect divided by the factored live load effect plus the impact factor, the dynamic effect. So essentially, the rating factor represents the remaining capacity for live load. Now, the way we deal with load testing for load rating depends whether we're looking at diagnostic load testing or proof load testing. For a diagnostic load test, we are going to really identify better the live load effect. We're applying a known live load and measuring the structural response as a result of that externally applied live load. And for a proof load test, we actually have a direct determination of the rating factor. So the procedures that we follow is for a diagnostic load test, we first make our field verified model, and then we adjust it for rating. What type of adjustments do we need to make? Well, we have to keep in mind that any load carrying mechanism that is not reliable long-term should be removed. And we have to, of course, include the right material factors to be using the design values of our materials instead of the average values which we use for comparing to the test results. And then for a proof load test, we do the load rating with these expressions that we have here from the AASHTO manual for bridge evaluation, which is the rating factor after a proof load test, which is a function of this value OP, which is a function of the proof load that is applied. K sub 0 is a factor that determines whether the proof load test was successful, and then K sub 0 is 1. And if the proof load test was stopped prematurely because of seeing nonlinear behavior or indicators that further loading would cause damage, then K sub 0 is 0.8. And then X sub PA is the factor that we use for applying finding the target live load. And that one is typically 1.4, but there's a number of correction factors that you can find in the manual for bridge evaluation. Once I have OP, I divide that by L sub R, which is the vehicle weight, multiplied by 1 plus the impact factor. Now, with that said, we've introduced the topic of load testing and the types of load tests that one can have. And then, especially for existing bridges, there is often the question whether a load test is feasible and whether it's a suitable way for assessing the bridge. So there's a number of things to discuss here. The first and foremost consideration here is to define and coordinate with the bridge owner the objective of the load test. If you do not set the expectations clear from the beginning, then you cannot prepare the test in the right way, and you cannot analyze the data to answer the open questions that you have about the bridge. So before starting to explore the application of a load test, we need to know why should we load test the bridge. One possible objective is to generate a field validated analytical model of the bridge that then can be used for load rating. We also may be interested in evaluating the effect of material deterioration and degradation on the structural behavior. An example of this is you could be interested in load testing, a proof load testing, a concrete bridge in which we have alkali silica reaction because of the uncertainty on the capacity of structural elements with alkali silica reaction damage. We may as well be wanting to evaluate rehabilitation or repair action. It could be because we have a historical bridge that we want to analyze. It could be because we want to determine if there are any additional load carrying mechanisms or load paths that take place in the structural system. It could be because we are using new materials and we want to check if they perform within the structure as expected. It could be for the estimation of remaining fatigue life. It could be to verify the behavior of a new bridge prior to opening. It could be to measure dynamic properties. And as I said, I'm not going to go into dynamic properties and measurements of dynamic properties because that's a whole separate field. Or it could be to verify any other aspects of performance of the bridge. But it needs to be identified before the start of preparation of the load test what the objective is going to be. Because once we know the objective, then we can start to think about the load application. Where are we going to apply the loads to get the responses that we need? And how are we going to measure them? So then we can think about the sensor plan. And before going into the step of actually testing the bridge, we need to evaluate if a load test can meet the test objectives. And here I'm going to take a side step by saying we also need to consider load testing as embedded within the philosophy of the levels of approximation, which we have in the FIB, in the International Concrete Federation Model Code. So the FIB Model Code 2010 is the model code of the International Federation Concrete for concrete structures. And that is the code that introduced this principle of levels of approximation. And here the solution strategy that they show is we have different levels of approximation, which have increasing levels of accuracy, but also take increasingly more time. So for example, they have applied this in the shear capacity equations in the model code 2010. And we see that level 1 may be very suitable for a quick preliminary design, whereas level 2 and level 3 are increasingly more complex and require increasingly more input data. And then ultimately level 4 may be much more suitable for an analysis of an existing structure or any particular sensitive application where we would require a very detailed understanding of the shear capacity. Now, if we apply that to rating and analysis of existing bridges, and I have particularly looked at slab bridges and the shear capacity of these slab bridges for the reason that these are the types of bridges that I have been studying since the beginning of my doctoral studies. And originally, I looked at really the shear capacity with the types of experiments that you see here. But over time, I got involved in load testing of these type of bridges. And the reason why I have focused mostly on these bridges is that in the Netherlands, this is a very common bridge type. They were designed in the decades following the Second World War with the design codes of that time. And if we analyze these bridges with the current Eurocodes, we find that they do not fulfill the code requirements for shear. And that's for two reasons. First of all, the shear capacity that the Eurocode prescribes is lower than what the old Dutch code used to prescribe. And on the other hand, of course, the live loads are not the same anymore. The live loads that they were designed for in the 1950s are, of course, much different from the current traffic situation, which involves much higher truck loading and much more frequent truck loading. So that's the reason why we are particularly interested in the Netherlands in the shear capacity of reinforced concrete slab bridges. And we used the levels of approximation from the model code to actually see how we can come up with a strategy to assess these type of bridges. And our first level is a quick hand calculation, which has been programmed into spreadsheets to be able to pass the whole stock of these bridges through the spreadsheet. And that's called a quick scan. As the name says itself, it's just a quick verification. And that helps us to already separate the bridges that fulfill at a basic level the shear requirements from those who may require further studies. And then we look at the second level, which is using linear finite element models to have a better understanding on what happens on the loading side. Now, the capacity side remains the same. Now, if we want to further fine-tune the analytical calculations, what we could do is either make a nonlinear finite element model of the bridge or use probabilistic studies. But the reason I put that in italic here is that many times we have uncertainties on the input that make it impossible to do this type of refined analysis. Examples of this are bridges where we do not have all the plans, bridges for which we don't know the material properties very well, or bridges where, for example, we have the effect of deterioration or damage that is much more difficult to model. So then we get to the most specific application or load level or level of approximation for, which would be field testing and actually measuring the actual response of the bridge. And that's in many cases load testing. And for these particular bridges, in many cases, it is proof load testing. Now, with that explanation of how we see load testing in the Netherlands as embedded within the assessment strategy, it's also important to do a cost-benefit analysis of a load test, especially for an existing bridge. You want to calculate the life cycle cost of the load test, which is consisting of these different elements. And there is the, of course, the initial cost of the structure, the expected maintenance cost, expected inspection cost, expected repair cost, and cost of failure. This is the expected cost of any bridge. Does not consider the effect of load testing yet. If we then include, for example, the cost of monitoring, and the reason why I include monitoring and not load testing is that there are no codes at this moment and no guidance documents that include this cost-benefit analysis for load testing, but we could make similar considerations as for monitoring. And in this case, we, of course, have the little stars on all these elements, which means that the cost of maintenance, inspection, etc., is going to be different because we are now going to add the action of monitoring, which has its cost, but may reduce, for example, the cost of, may require less frequent inspections, for example, so changes the cost of inspections. And the tendency in these cost-benefit analyses are to calculate the cost not based on the economic cost, but add in the environmental and social factors. And what we see for bridges more and more is to actually analyze a decision with regard to load test or not a bridge by looking at the impact of, for example, posting the bridge at the network level of the road network and infrastructure network. So to summarize, there is a number of steps that one goes through to identify if a load test is feasible. Important there is to look at the level of uncertainty that is involved in the current rating of the bridge. Very important is to identify the objectives of the load test and see if the execution is possible. And then also see if load testing is a cost-effective method to know more about the bridge by doing an analysis of costs and benefits. So a few general considerations for load testing. First of all, the preparation of the load test means that we need to define the objectives, as I talked about before, and then we also need to have a look at the live loads that the bridge is designed for, or that the bridge should be carrying according to the code that is ruling. So we need to look at a combination of distributed and concentrated loads, especially if you look at the load models that we're using in Europe, which you can see here. And we need to define for which load model and which safety level we are going to prepare the load test. We also need to know more about the bridge. First of all, we need to have an inventory of the available documentation. And then we also, I really recommend to go see the bridge before preparing the load test so that you can have an idea of, first of all, we need an inspection to know if there are undocumented section losses or deterioration, which of course would influence the rating and potentially influence the way we carry out the load test, as a different member may have become critical. Then we go into the preliminary calculations, such as the load rating, predicted capacity, and this is generally what we use for existing bridges. We also need to have an idea of the material properties, either from the available documentation or by taking samples of the materials, such as concrete cores. Then we need to set up the analytical model to prepare for the test, and depending on the type of test, also use the model then for assessment of the bridge afterwards. And in many cases, we may as well be interested in supplementing the inspection with non-destructive evaluation by having a better, which allows us to gain more information on the condition of the bridge. Other practical elements that we need to prepare is the position of the load, which could be limited to 1 or 2 positions if it's a proof load test, or multiple load paths and load protocols in terms of driving when we have a diagnostic load test. We also need to define the magnitude of the load. As I said, this has to be a load that corresponds to the factored live load in case of a proof load test, and it should be representative of typically 60–70% of the live load when it's a diagnostic load test. And many times this preparation involves the use of an analytical model, a linear finite element model. And then there's practical things to think of as well when preparing a load test. First of all, your inspection prior to the load test is crucial to know if there's any side limitations, such as whether you cannot access parts of the bridge because of the bridge being over water. Other site limitations means that it could be that the sidewalk is a little bit higher than the road, and you cannot apply sensors, you can't measure well because of that elevation. Other site limitations may mean that there are some type of cables of electricity or whatnot that you are not allowed to touch or need to stay away from, or environmental considerations, habitat of endangered species that should not be disturbed, or potential weeds or plants that may be dangerous when you touch them. So that is crucial information from the inspection that may mean that you need to adjust potentially the way you're going to apply the sensors, the way you're going to apply load, and that may mean that there are certain safety considerations that are very important for during the execution of the test. Of course, I cannot stress it enough that your preparation should be very well aligned with the test objectives. And then when it comes to the interpretation of sensor output, we need to know beforehand what we're going to, and which information we're going to need during the test from the sensor output. So for example, during a proof load test, we're going to need to know what the sensor output means in terms of stop criteria. So we need to have predefined the stop criteria and translated that into magnitudes of sensor output. We also need, for safe execution, a safety and risk plan. In some cases, it's also very important to coordinate with the road authorities in terms of safety with regard to bridge closures, etc. And of course, there's a lot of things that one needs to do during a load test. So a detailed planning of activities and assigning roles to all people involved is crucial to make sure that everything can be done in the amount of time that one has available. So sometimes you get just a night in which you can close the bridge and carry out the test. In some cases, we have had proof load tests that were more for research, where the Ministry of Transportation could close the bridge for 1 week, and we could carry out a number of tests and apply the sensors with a little bit more time, but that's not always the case, of course. And then when we look at the instrumentation plan, we need to know, of course, what we're going to measure, and what we're going to measure has to be strongly aligned with the objectives of the test. So that could be longitudinal and transverse deflection profiles, deflection at the support, strains at, and I put here at the bottom of the slab, could be at the bottom of the cross section, strains caused by temperature and relative humidity to subtract the environmental effects from the strains caused by the applied live loads, opening of existing cracks, if there's any existing cracks, development of new cracks. Also want to carefully monitor the applied load. And then some of the elements that we are currently using for research are acoustic emissions, which we can measure for research purposes. We also are exploring the use of taking photographs and doing digital image correlation to get information about strains and deflections and cracks, as well as monitoring with optical fibers, which is as well something that is of current research. We also need to think about how we are going to do the data acquisition and how the details of mounting and wiring are going to look like. And for any crucial measurements, it would be important to also have redundancy in there so that if we have sensor malfunction, we can still answer the open questions and fulfill the test objectives. So even though we try to minimize the applied sensors, a bit of redundancy, especially for crucial measurements, can go a long way. So when we talk about data acquisition and visualization, there's a number of things to consider there. Your sampling frequency has to be in line with the way you apply the load. So if you're going to do a diagnostic load test and the vehicles are moving first at crawl speed and then perhaps at several speed levels, then of course your sampling frequency has to be such that it is fast enough to gather the data in relation to the moving of the trucks. We want to have real-time measurements, especially for proof load tests, so that we can check core stop criteria during the test. And needless to say, but important and something that sometimes is forgotten as well, it's important to calibrate all your sensors before the test. Then in terms of personal requirements, generally, there has to be one responsible bridge engineer, and depending on the international code that you look at, there's requirements, for example, that it has to be a licensed professional engineer. We also need to have enough people on site for tests and traffic control, and there may be additional requirements by local agencies and bridge owners for personnel. And I already hinted at the fact that the environmental effects can be important. We know that certainly in diagnostic load tests, if the weather conditions are such and the duration of the test is long, that the environmental effects can be sometimes in the same order of magnitude as the effects of the externally applied load. So we need to understand very well the effect of temperature and humidity. Most cases, it is temperature that gives the largest changes. And the effect of temperature and relative humidity is actually twofold. We have the effect on the structural response, which means that there will be stresses generated in the structure because of the changes in temperature. And one way that we can mitigate this is by using a so-called dummy sensor. So instrumenting a part of the bridge that is not going to be subjected to the applied loads during the load test so that we can measure there the effect of temperature and humidity. And it could also be by having some no load cases. So by having, for example, a day of measurements in which, and that of course requires a longer closure of the bridge, a day or a certain number of hours of measuring the strains without having any external load applied. Then, on the other hand, temperature and relative humidity also affect the sensor. And the way you can mitigate that is, first of all, selecting a type of sensor that is not so sensitive to temperature and humidity. And if your sensor is sensitive to that, you can correct your readings with information from the manufacturer. It has to be in the information sheet of your sensor. And what you can see here is some measurements that we took on a bridge with ASR damage, and you can see that this is temperature variations over multiple years, but we also see that that caused strain and stress effects in the bridge itself. Now, typically, the duration of the load test is so short that within that amount of time, the bridge doesn't really get the time to react to temperature and humidity. But if you're going to do multiple load tests, or if you're going to load test over a day or 2 days, this may be something to consider. Or if you start very early morning when it's still dark, and then you continue on into daylight, and you get the warming up and the irradiation of the sun, then you may get more effect. That brings us to the step of the execution of the load test. And what I'm showing here is execution of a proof load test, which is what we have been focusing on in the Netherlands for the reinforced concrete slab bridges. And for load tests, proof load tests, what we recommend is to use a loading protocol that would look something like this. So we have variable cycles in there. And the reason why we have cycles is, first of all, to check if the behavior of the bridge is linear. So if at the second cycle, we still have the same structural response as in the first cycle. And secondly, to check the reproducibility of the measurements. You also see that the load doesn't go to 0 in this loading protocol after the cycles. And that's because we want to have a minimum load during the test, because we apply the load with hydraulic checks and we want them to remain engaged. And the load levels that we recommend is first a low loading level that just serves the purpose of checking if all the sensors are giving reasonable measurements. Then we have a load level that corresponds to the serviceability limit state. So if you look at the applied load, the target proof load, as a factored version of the live load, then the factor in this case would be 1. Then the ultimate load that we have is our target load level. So that's with the load factor included. And then we also want to have an interim level. And the reason why we have all these steps in here, and as well as here, is that whenever we increase the load, we want to be very careful and check the stop criteria to make sure that further loading is not going to cause damage to the structure. And in the last step, we are going to analyze the test results. Of course, we have the real-time monitoring of the responses for proof load testing to check the stop criteria. But at the end, we are going to analyze the measurements in detail. So we're going to correct the influence of temperature and humidity if we've observed it. We're going to correct for the support deflections, and we're going to generate all the figures and information necessary for the final report. And then ultimately, what we want to give is a recommendation that essentially gives an answer to the open questions that we had about the bridge that is in line with the test objectives. But of course, the ultimate decision on how to manage the bridge in light of this information lies with the bridge owner. Now let's have a look at the difference between load testing of new versus existing bridges. There's of course difference between new and existing bridges. In a new bridge, we want to check if the bridge is behaving as it was designed. This is a standard requirement in many countries, such as Spain and France. And since the bridge is newly designed, we have information about the bridge. For existing bridges, there can be various objectives, as I talked about. We want to determine the load rating. We have the manual for bridge evaluation, as well as the new TRBE circular that we can use as guidance there. And we may not have all the information available. We can have different levels of information, and there can as well be the effect of deterioration on the existing bridge. I'm going to show you some results of load testing of a new bridge. This is the Los Pájaros bridge in Quito. And this bridge was load tested because it's the first steel bridge that was constructed using the incremental launching method in the city of Quito. So since this was this was the first time this construction method was used, there was there were some concerns whether this would work well. So the objective was to verify the design assumptions and prove that the bridge behaves as designed. And the load level that was applied was 60% of the AASHTO HL93. So here is the longitudinal and sectional view of the bridge. You can see it has 3 spans of 65 meters, total length of 195 meters. And you can see that it crosses a very deep gorge of 38 meters in depth over the Monjas River. And in cross-section, it has 2 parts, one that consists of 4 girders and one that consists of 5 girders. You can see here a photograph of the bridge during construction using the incremental launching method. And the load test served as a validation of the model that was used for design. You can see here a photograph of some different truck paths, one of the critical truck paths that was used to check the behavior of the bridge, the responses of the bridge. The measurements, there's not a full instrumentation plan here. This was a simple it was a verification type of load test. So the deflections were measured with total stations. And what we have here is a comparison between the output of the finite element model that was used to design the bridge and the measurements. And as I mentioned, the measurements were from total stations. So there's some measurement uncertainty on that. So comparing those computed and measured results, we can see that there's a good correspondence between the model and the measurements. So the bridge performs as designed. And the conclusion then was, yes, the bridge can be opened to traffic. Brings me to the topic of international use of bridge load testing. I already showed you an example from Ecuador and some of our applications in the Netherlands, but what about the rest of the world? So in Europe, there are several codes for load testing for various types of load testing. There's the German guideline, which is really for proof load testing of existing buildings. There's a Spanish code for load testing of new bridges and a French code for load testing of new bridges, as these are countries that require load testing prior to opening. In the United States, there is the ACI 437.2, which is for proof load testing of buildings. For bridges, there's a manual of bridge rating through load testing, and that's also contains a bit more information than the manual for bridge evaluation, but the concepts are the same. And then the most recent document is the e-circular of the Transportation Research Board on bridge load testing. Most of these codes and documents really just look at flexure in concrete. And as I mentioned before, in the Netherlands, we have concerns about shear, and none of these look at the effect of existing cracking or deterioration. Load testing and codes and guidelines for load testing is a topic that is very relevant internationally. There are a number of documents that are under development or under preparation. But in the ACI, there's more documents to be expected from the Committee 437, load testing for buildings, as well as 342, which is working on a document for condition assessment of bridges, which will include load testing. In the Netherlands, we are doing research on the topic. The FIB, the International Concrete Federation, has developed a bulletin on the assessment of existing structures with included load testing, and the new model code potentially will as well include a part on load testing. And we very recently joined efforts to develop an international committee under the umbrella of IAPMAS for bridge load testing to have a venue to share our experiences. And in various conferences, we've had sessions with researchers that look at this topic. The one that is coming up is the IAPS Gent, where we will have a session on assessment, and we'll talk about some load testing applications. And we as well are preparing a session for IAPMAS in Spain in 2022. Some documents, international documents that may be of your interest is the ACI SP 323, of which I was a co-editor. That's titled Evaluation of Concrete Bridge Behavior Through Load Testing, International Perspectives. And this collection of research articles on diagnostic and proof load tests on bridges, which I developed with Dr. Katbas, is as well available freely online. So all the articles are open access. I'll be happy to share my slides later on, but if you go through this link, you will get access to all the articles. So there's 15 articles in total that are freely accessible. I also had the privilege of being the editor of 2 books on load testing of bridges, one on current practice and diagnostic load testing, and the second on proof load testing and the research tendency, which were published 2 years ago within the series of structure and infrastructures. And then I mentioned before the e-circular of PRB, which was developed by a working group within PRB AKB 40. And again, this is a freely available document. So with the link that I have left here in the presentation, you can download the PDF directly if it's of your interest. So with that said, I wanted to give you an idea as well on the research that we've been doing in Delft, and we've carried out proof load tests since the early 2000s. There were first 2 where we were not that involved, but from 2013, we have been involved and carrying out research on this topic. And the 2 bridges that are here in italic are actually collapse tests that we got to carry out. So this amount of loading that you see on this photograph here is not the amount of loading that one would need during a proof load test. This is what we applied in a collapse test. So I just think it's a very insightful picture because it shows the amount of counterweights applied. So just an example, we tested a viaduct Zeilweg, which was one of these shear critical reinforced concrete slab bridges with alkali silica reaction damage. And the question there was, we know from experiments in our laboratory that the shear capacity of these ASR damaged structures is only 75% of the shear capacity of a non-damaged concrete. But there were some concerns whether that 75% is correct, because in some cases we also found results of experiments where the shear capacity of ASR damaged elements was higher than those without damage. So for that reason, we did proof load testing for flexure and shear. We had the opportunity to close a bridge for a week. It's a viaduct over the highway, so there were some limitations in what could be done as to not disturb traffic on the highway. We used measurements with laser, acoustic emissions, and LVDT. And finally, we could show with the test that the bridge can carry a load that is equivalent to the design live load. Another bridge that we proof load tested is a viaduct de Beek, which is a viaduct that did not have material degradation, but you can see here already from the photograph that it has important cracking from overloading. Now, this one was more complex because it's also over the highway, and we could only test the first span, as the second span, the crucial span, was over the highway. We tested for flexure and shear, and our ultimate finding was that if we allow for 7% plastic redistribution, then the bridge can carry the live loads from the code. But since we are allowing plastic redistribution, that means more cracking, etc. So in this case, it would be really important to have inspections to check the durability and as well check if there's no ongoing corrosion in the structure. And with that, I'm going to show you a time lapse of this load test. So let me stop sharing my screen here to bring up the video that I will share with you. do have to synchronize quickly here the video.
You have to share the video, Dr. Lanza.
Yes, just a few moments as I am using a different computer and I have it in my Dropbox folder, but it was not synchronized onto this computer. So it takes a moment to synchronize. I will continue with the presentation and then I'll show the video at the end. My apologies for this.
No problem, no problem.
It's a 500 gigabyte video. It takes a moment to synchronize. My apologies. So something about our current research, we are particularly looking at the moment at shear stop criteria for proof load testing of reinforced concrete slab bridges. May sound as a very specific or very niche topic, but since we are so interested in testing these reinforced concrete slab bridges in proof load testing them for shear, there's of course the risk of a brittle failure during the load test, and we want to really develop reliable shear stop criteria that are based on shear theories. So we are looking at the development of cracking and everything that gives indicators of shear failures before failure. So we're simulating proof load tests with laboratory tests, and we're applying different types of sensors to monitor the structural behavior. We want to propose stop criteria based on theoretical understanding so that we can come up with recommendations for proof load testing of concrete bridges. And here you can see some drawings of the test setup. The slabs are 30 centimeters thick and they're 5 meters by 2.5 meters in length and width. And you can see that we are measuring the support reactions here. And these slabs are representative of continuous slab bridges. So to avoid having to build multiple span slabs in the laboratory, what we do is we apply these Dweck pre-stressing bars here to create a bending moment over the support and essentially have similar behavior to what one would have in a continuous slab. So that's what you see here at the continuous support. In terms of instrumentation, we're applying lasers to have the longitudinal and transverse deflection profiles, as well as LVDTs, linear variable displacement transducers, to get the deflections and strains, deflections at support and strains at the bottom of the slab. We're also using digital image correlation for cracking, as well as to look at displacements and strains, as well as acoustic emission sensors to get an idea of internal cracking and what's really happening internally within the slab. And ultimately, we've also been applying optical fibers in the reinforcement itself and glued to the bottom of the face, to the bottom face of the slab to measure strains at various points along the length of the rebars, as well as along the length of 3 lines of the bottom of the slab. And then the loading protocol that we apply is very similar to what I showed you before in terms of loading protocol for a proof load test. That's the red part here. And then we have multiple levels more until failure, where we really want to study the stop criteria and on ensuing failure. So here is an example of the results for one of the tests that we did. I should say of a number of tests that we did, but with here the results of the first test that we did. So you see the load displacement graph for a number of the slab tests, the different positions on the slab that we tested. And here you can see the results of the strain analysis from the digital image correlation, which after failure you have this large punched part on the bottom of the slab. The failure mode here was a flexure-induced punching. So to summarize, we've looked at both diagnostic and proof load testing, where the test objectives are important, the measurements and planning is important. Load testing can be a cost-effective way to evaluate existing slab or existing bridges. And we are currently carrying out research on particularly to improve the procedures for proof load testing of reinforced concrete slab bridges. With that, I would like to thank you all. And before we continue, I will try to see if I get my video working now to share with you the time lapse of the load tested that I have pending here. Let's see. Now I can open the file, share my screen, and make this full screen. And you should be able to see my screen now with the video.
Yeah, yes, we are able to see.
So what you'll see in this video is a time lapse of a proof load test that we did on viaduct to bake. And this is starting very early in the morning when it's still dark. And you can see that the bridge is over the highway. Here you can see the instrumentation that we applied. And we do use the wired sensors, as most of our work is typically laboratory work. So you can see the LVDTs and acoustic emission sensors. Here's a close-up of an LVDT.
Video is not moving, I think. Did we lose connection with her?
Video has stopped.
I think we have lost connection. She will join back, I'm sure. Oh,
I think we lost connection with her.
yeah, we lost connections. Let us wait for 1 or 2 minutes. I'm sure she will join back. But what a fascinating presentation it was.
Well, it was a very structured presentation.
Very, very structured.
I think somebody from the audience observed that it is more like a speech and not like a lecture. But I thought it was more like a lecture,
Yeah.
more like a class lecture then.
Yeah. I think by the time she joins, let me just initiate a discussion on this, that, you know, what I find from the presentation of Dr. Lansot is that it is very different from what is prescribed in our codes. So yeah, I think she has joined back. Dr. Lansot, you are back.
My apologies,
So
Zoom threw me out of the meeting.
Yeah, no issue, no issue. This routinely we face this. So kindly share your video once again. Wherever you left in between.
It could be because it's a very heavy file, so it's uploading on my side and downloading on your side. But I will try it again, and please let me know if it doesn't go through.
Yeah.
Open the file again. Can you see the video coming through?
We can.
Yes, we are able to see.
So this is a time lapse of a proof load test that we did on viaduct to bake. You can see the mounting and wiring of the sensors on the bottom face of the slab. There's a close-up of an LVDT. And we are measuring longitudinal transverse deflection profiles as well as strains on the bottom.
Mhm.
You can see here as well an acoustic emission sensor, which we use for research purposes. The last preparations on the bottom face of the bridge, and then we go to the top to apply the load, which are the 4 wheel prints of the Eurocode live load tandem. So we want to make sure that everything is well aligned and straight. So we use a layer of sand, this wooden plate, and then the actual steel loading plate on which we then apply load cells and jacks. You can see here the load cells that measure the applied load on the 4 wheel prints. Some views from the crane as well. And what we use in the Netherlands for proof load testing is this system with hydraulic jacks and counterweights. And this for us is a feasible way because we use heavy lifting equipment that is available in the ports. So it's a short distance to transfer that to the sites where we will be load testing a bridge. We have also worked with the load testing vehicle from Germany, but then the difficulty sometimes is that the vehicle lives in the very east of Germany and it has to get permission to pass all its bridges on the way to the Netherlands, which sometimes then this way of building a proof load testing setup, which may look a bit convoluted, actually turns out to be a more feasible solution for us. You can see that during the tests, we measure all the structural responses real time. And as I said, we use this heavy lifting equipment. So the load is applied through the hydraulic jacks with oil pressure. Here you can see some video from during the test itself. This is a manual load application and our measurements during the load test itself. Here are the real-time measurements that we have. And then verification of cracking when the load is not applied on the bridge. Further application of counterweights. You can see here this sped up video that the bridge really moves downward and upward as the load is applied. As I mentioned, this is a time lapse of 1 day of load testing. So you can see that we started in the dark and this was a successful load test. So we ended in the dark with a successful test. And with that,
thank you.
Thank you.
Thank you.
Thank you very much, Dr. Lansford, for such an excellent presentation, practically covering very holistically, all aspects of the load testing in a very structured manner. Several takeaways from your presentation. Firstly, you have very rightly in the beginning itself mentioned the need to have a clear objective for load test. One should know beforehand why we want to have the load test, how should it be done, what is the acceptance criteria, and whether it should be a proof load test or a diagnostic test, what should be the load to be applied, all these things have to be, sort of done beforehand, the exercise. Also, another takeaway which I found is that you mentioned very well, very nicely explained the importance for the preparation, before the testing, and depending upon the site situation, how to decide on the methodology of testing as well as the other instrumentation. Particularly the last part I like very much about the codes on load test, how you have practically given us the current scenario of international codes, what are the practices in different countries, and also your future research that you are working on. Overall, on the whole, I think the participants would have got practically a holistic picture of the state of the art on this. So thank you very much. Now I would go to the panelists, and I begin by requesting Mr. Amitabh Ghoshal to give his views on this excellent presentation by Dr. Lansot. Mr. Amitabh Ghoshal is a known personality. I don't think he needs to be introduced to this audience. He is a pillar of structural engineering in India. He has, to his credit, several mega projects, and I would not like to say more about Mr. Ghoshal. Mr. Ghoshal, floor is yours.
Well, it was attending a thorough lecture, giving all the aspects of load testing, and both dynamic and static load tests. You see, the later part, you have dealt more on static load testing, where a lot of measurements could be sort of made, analyzed, and at the same time compared. What is very common in our country is to carry out dynamic load testing after completion of a bridge, and also when you are testing an old bridge, because invariably very limited traffic stoppage is permitted once a bridge is open. So that provides a limitation. Now, there are a few things I would like to learn. You have mentioned about acoustic emission test. And you had shown also how the test is done. But exactly what are the features that an acoustic emission test indicates? That is number one. Number two, you have mentioned in your presentation about, in the objectives, how to estimate remaining fatigue life, or for that matter, remaining life of a bridge. That's a very important aspect when we test an existing bridge. Now, a little bit on that, because you have not later explained about remaining fatigue life or remaining life of a residual life of a bridge. Relative humidity is something we had not been measuring. Temperature correction, yes, but relative humidity, it affects, I can imagine, it affects the concrete slabs, concrete bridges. But in a major bridge, is relative humidity of any concern? Of course, not in steel bridge, but even in long span concrete bridge or in pre-stressed concrete bridge, will relative humidity be an important factor? Well, I can go on asking questions, but I don't think that is fair. I have given you 3 questions. If we get answer to that, I'll be very, very obliged. Maybe you may want to answer these questions now, or you would like to listen to the other panelists and come back later.
I think it is better to answer the questions right now.
Yes,
so
yes.
That...
And I have reflected some of the concerns which have been expressed by people who have sent chats and questions. I have tried to take from there.
Yeah. Over to Dr. Lansot, please.
Well,
Over
thank
to
you
you,
for
Dr.
these
Lal.
excellent questions. Let's start with the acoustic emissions. And of course, what acoustic emissions measure, or what the acoustic emission sensors measure, are acoustic emissions or sound waves. So the way to relate that to structural behavior is not that straightforward. We know that if a crack opens and there is tension effects, that causes acoustic emissions. We know that when there is friction in a crack, that causes acoustic emissions. But it's still a topic of research to actually say, now this means that there is a flexural crack, or this means that there is a shear crack, or this means that we have to worry about the bridge. So we have a doctoral candidate who is actually right now working on linking acoustic emission measurements to the actual structural response indicators. What we generally can do, and what we've done in the past when we have these acoustic emissions, is when we see that there's a lot of acoustic emissions above a certain threshold, we know that there is a lot of cracking activity. And if that cracking activity suddenly increases, we qualitatively know that that means there is the development of a crack that we may want to capture with either one of our LVDTs of a crack that we are monitoring, or that we want to remove the load and go check under the bridge if we are observing any cracking. But really to quantify that into structural response, that is a topic of our ongoing research. Then with regards to remaining fatigue life and remaining life of the structures after load testing, that's as well an excellent question. In terms of remaining fatigue life, that typically is related to measuring stress ranges and structural responses associated with that. Whereas when we talk about remaining life, that actually brings us to the field of the of structural reliability, because essentially we want to have not just a safety level, but a safety level with a period of time associated to that. The way we are currently dealing with that is we apply the proof load that causes the same structural responses or the same bending moment or sectional shear as the factored live load combination. And then we, depending on the load factors that we use that have been calibrated for a certain amount of life, we say, well, that then relates to, for example, this period of 15 years, 30 years of future life. But if we want to do this really in line with the principles of structural reliability, then it's important to actually link the target loads that you are using to the annual probability of failure and the probability of failure over time, which decreases because you have ongoing effects of degradation. So typically, if we look at our reliability index, we reflect it as something that decreases over time and maybe have a steep decrease if we start to use a different load model. So the correct way of estimating the remaining amount of years until we reach the minimum reliability index that the code allows would be by doing a probabilistic analysis. And then the third question with regard of relative humidity. In my experience, it is in the Netherlands, of course, we do not have large changes in temperature and humidity during the day. The weather is generally humid throughout and the temperature doesn't change much between day and night. So we have not measured large effects of environmental effects on the during the load test. The time that we have that we take for a proof load test, which is a maximum 2 hours, is also a short frame of time to really see a structural response as caused by temperature and humidity together. And if we take humidity separate from that, typical climates will have more changes in temperature than it has changes in humidity. It would be very strange to go from 20% relative humidity to 80% in a single day. So the temperature effect is the larger one of the two. And in my experience, these effects are limited for load testing, but if we do long-term monitoring, that of course becomes a more important effect.
Thank you.
Thank you.
Thank you for answering all the questions. I'll just ask you one more question. That is, do you measure the stress directly? You by putting strain gauge, you are measuring the strain, but can you convert it into stress and the meters which have been applied? Of course, it is possible, possibly in a static load test, but I'm not sure that in a dynamic load test, you can also have the stress measurement directly. I would like to be enlightened.
We focus on strain measurements, and indeed, what we measure is a strain and not a stress. We could convert it to a stress, but that's of course a calculation step.
Yes.
And with strain measurements, you may have seen that we apply these LVDTs. So we are actually measuring an average strain over a certain length. The reason why we do that is, of course, you would have a different strain measurement if you're right at a crack as compared to next to it. So we average it over 1 meter, half a meter, to actually have something that is a smoothed strain measurement. And that's what we use for proof load testing.
Thank you.
Dr. Lansot, I have a question before I go to the next panelist. In every code on load testing, even including our own Indian Road Congress code, there is an acceptance criteria which is related to the deflection. I mean, the theoretical deflection vis-a-vis the deflections that you measure during the load testing. And there is a permissible limit of exceedance in the deflection. In some countries, it is deflection at the load test is not permitted to exceed the theoretical value. In some countries, they do permit. In Indian Roads Congress Code, for proof load testing, the allowable deflection in load test is supposed to be less than the theoretical value. What is the international practice in this regard, if you can enlighten us?
Sure, that's an excellent question. And we see in virtually every code and guideline for load testing that deflection is used as the structural response of reference. And the reason why we look at deflection is, of course, that's the most practical one to measure, as I showed with the example of the load testing of the new bridge. Applying a total station is a much more cost-effective way than having to build a setup to apply sensors, as you've seen that we do in our proof load test. Now, we have done some additional testing, laboratory testing of beams, and now we're testing slabs subjected to cycles of loading to see what we can learn from deflection. And of course, deflection, if you look at deflection as a structural response, it's it's 2 integration steps away from really what is the strain in the cross section. So there's a lot of elements that are involved there that make that deflection measurements, depending on the objective of the load test, may not be the right response to measure. And I say this very carefully because when it comes to stop criteria for proof load testing, we find that based on our experiments that the deflection criteria from the ACI 437, for example, or the German guideline, they do not give a good warning sign for as a stop criterion in the proof load test. But on the other hand, we also, so for really the avoiding large damage to a structure, deflection may not be the right response to measure during a proof load test. But on the other hand, I also do not want to say, no, deflections are not the measurement that we need, because we know that for certain types of load tests, having a quick setup, for example, with the total stations to just measure deflection lines is going to give us sufficient information. With that background, to say how much difference we should allow between the analytical model and the measurements is as I already hinted at in my presentation, is a function of the error on the measurement in the first place. So if we're going to measure with total station, we're going to have a different error on the measurement as compared to when we would be instrumenting the bridge with optical fibers and measure it. Well, that would give us strains. If say we would put a number of laser distance finders at different positions and have the deflection profile from that, it's a different inherent error on the measurement that we have there. So from that perspective, the permissible exceedance that we have in the codes, we see that in Spain, for example, there is just a general permissible error in their code, whereas other countries say this has to be judged by a licensed professional engineer, just because there's so much involved with that related to overall structural response, type of bridge that we're looking at, measurement technique, that sometimes quantifying that with a certain percentage may be a bit tricky.
So it is left to the basically engineering judgment of the professional engineer who is involved. Very good.
Mm-hmm.
Okay, so now I would move to our next panelist, Mr. Jayagopal. He, as I mentioned in the beginning, Mr. Jayagopal is a managing director of a firm called Structural Geotech Research Laboratories Private Limited. He has 42 years of experience, very widely respected in the profession. He is also a member of our code committee B8, which deals with load testing and assessment of bridges. He has executed several investigation of bridges and also performed several load tests. Over to you, Mr. Jayagopal, your views on the presentation that you have just seen and listened.
Yeah, thank you, Mr. Alok Bhomik. In fact, Mr. Alok, you remember about Landsat you were mentioning, I think about 6 months back only, some research and load testing have already been written, and it's in advanced stages. And when we were reviewing that IRC-SP 37, you mentioned many times about her name and her work actually.
Yes.
And anyway, finally today it has come to listen to her lecture. It was very interesting, especially certain points like no damage to the bridge. Normally what we see, now no damage, what in her points she mentioned, rating factor, elastic state and not getting into the plastic state. In fact, we have an IRC 37, clearly we write not to get into the plastic state at all. Then evaluation of remaining fatigue life, as our respected Mr. Ghoshal Saab has told, it's a very interesting one as far as the steel structures are concerned, I think, and we are not doing here. Then coming to the safety margins, it was very good. Difference between the theoretical and actual deflections normally, I think, will give the safety margins as far as we know, because we take the deflections as a primary criteria in the evaluation of the bridges in India actually here. Then the codes of different countries. In fact, the committee members were very much interested in the codes of different countries. Then as far as the research, what we are doing, it is fantastic. It is very advanced. And research, as far as we know here, we are not doing anything as far as the bridge load testing is concerned. Then coming to this 15 years, 30 years, etc. Normally what we do here, in fact, of late, we have divided the whole investigation of the bridges into two categories. One is the durability aspect of the bridge, and one is the load carrying capacity of the bridge. And we have separated these two aspects, and we separately talk about them when we do investigation to any of the structure. Because load carrying capacity, as far as we know, because I must have carried out more than about 1,200 bridge load tests, and lot of difficulties, lot of changes, lot of corrections. What we found has been incorporated in our codes, IRC codes. So what I feel with the bridge load test, this age of the bridge, looks to be a bit difficult to make out. Then regarding the instrumentation, your presentation was fantastic. So much of instrumentation, it was very, very good. In fact, a lot of things engineers will have to learn based on the knowledge from other countries, other engineers, other structural engineers. Of course, we are also catching up, we have already used under our Ghoshal saw, we have already used this fiber brag gratings for measuring the strains. Then we have used the advanced strain gauges, LVDTs, accelerometers, inclinometers, and of course, all under the real time only. All under real time, can be monitored from anywhere to anywhere in the country or outside the country also. And I would like to give you certain additional information of what we have done from last few years here. We take the temperature correction, that is thermal correction, as a very important factor. We have, of course, this humidity, we have not gone into humidity RH, but temperature, we take it very seriously because it is the factor which either goes into the approval or disapproval stage. Earlier, the thing is, it will not be possible to measure the deflections at particular time of temperature, as actual deflections will occur only after the core of the structural member attains the temperature. Example, the highest temperature around 2 p.m. in the day, whereas the deflections will be maximum around 9 p.m. night. This has been established for not less than about 200 to 300 bridges by us. So much of observing, then we put the clause in our IRC SP51, that is load testing of bridges, that a line joining between the least temperature and a least deflection and highest temperature and highest deflection, that will be a linear line, and in between whatever temperature comes, we put it for correction. This is what we are doing here in India. We have an additional problem that needs to be seen by our other panelists and as well as our Alok Bhome in metro load testings, metro rail. What they do is they load the bridge span for at least 7 days. Continuously, they keep adding weight 7 days. 7 days, and one day they will keep it like that only for 24 hours. Then offload 7 days because that is difficulty. But my feeling is, I have already told in many times to the metros that it is expected if you do like this, creep might set in to this superstructure and your pre-stressing strands may get loose also, maybe after some time. So be very cautious because we are not seeing such a thing, but 7 days is a too large a period for load testing of the structure, either loading or unloading. However, not to take much of your time, the lecture was very good, extremely informative, and of course, all the three of us, we are actually revising certain codes, and this information will be extremely useful in upgrading our codes also. This is my frank view. Thank you.
Thank you, Mr. Jayagopal. I think I will pose this question to Dr. Lansot. A very pertinent point which Mr. Jayagopal raised. In fact, I was also about to ask this question. Good that he has done it. See, you mentioned in your presentation several times that the actual load testing is for a very short period. So my question is, how do you decide? Because you also mentioned in some of your slides that some, depending upon the availability of the constraints at site or less constraints, the load testing can be prolonged. So how do you decide whether the testing would require only 2-3 hours or it should require 7 days, as Mr. Jayagopal mentioned? What is the rationality and what is the sort of reasons behind these decisions?
That's an excellent question. And to answer that, we can look as well at the ACI 437.2 code, because that's one of the international codes that actually looks at two types of loading protocols for proof load testing of concrete buildings. And the traditional load protocol is indeed one that involves building up the load and then leaving it there. And now you're testing my memory, but I think it's 24 hours, and then measuring 24 hours unloaded. 7 days is, of course, a very long time, and certainly concerns about creep, especially in pre-stressed structures, there become important. If you look then at the other loading protocol that the ACI 437 allows, that is what they call the cyclic loading protocol. And that's also the type of loading protocol that the German guideline is recommending. So I think traditionally, especially in buildings, loading protocols that involve keeping the target proof load for 24 hours or more was very commonplace. But nowadays with methods, with JAGs, we can use these cyclic loading protocols. And as you've seen, what we do is we apply these different load levels, and typically we just leave the load until the measurements are stabilized, which depending, it's a function, of course, on the type of structure, but it's in the order of minutes rather than hours. So the whole protocol of 4 load levels with 3 cycles per load level, that typically takes us roughly 2 hours to 3 hours in the field. Now the time of closure of the bridge for us is typically more a function of, you've seen the instrumentation that we use, and that's of course as well because we want to do research about load testing. So definitely for engineering practice, it's not necessary to spend days building that entire setup of instrumentation that we use, but we actually want to use as many measurement methods as possible so that we can come up with recommendations for practicing engineers, what is actually the most cost-effective way to do it. So that's also the reason why for research purposes, we tend to, it's very convenient for us if the bridge can be closed for a week, because then we have a few days to apply all the instrumentation, and then we have 1 or 2 days to do or 2 load tests that the load test itself takes 2 to 3 hours, but of course there's the time of building up the setup as well because of the equipment involved. And that of course changes if you would use a load testing vehicle. As I mentioned, we also have done load tests with a vehicle that came from Germany, but then the limitation that we have is that it has to get all the permits to cross all the bridges on its way. So that's a consideration between time and cost and speed that we have to make on an individual case.
Thank you, Dr. Lansot. I think it's already 8:40 here, so it is really time to close. But I think if you don't mind, if you can pick up 2 or 3, maximum 3 questions from the Q&A box and respond. If you can do it yourself, or if you want me, I can read, but I think it's best if you choose any 2 or 3 questions to respond.
I only see 5 questions in the Q&A box since I lost connection at some point. So anything that was posted before that, I cannot see. So perhaps you could pick a few questions from me.
So I can because
actually,
there
5 is the number of chat. The question is 17.
There are 17 questions, but let me pick up, maybe because you joined subsequently later, so you lost few questions. So let me pick up. There is a question from Mr. Dinesh Kumaran, who says, how would you calibrate your finite element model to simulate material degradation in an aged bridge? Does it usually involve modifying the material properties in your model until it shows similar behavior with the field test data?
That is an excellent question. And it, of course, depends on how advanced you want your model to be. The most straightforward and at times cost-effective step would be reducing de Young's modulus. For example, if we have a bridge that has significant cracking in the transverse direction in the slab, what we could do is to actually use a different de Young's modulus in the longitudinal direction as compared to the transverse direction. So we would use a much lower E modulus in the transverse direction that represents the amount of cracking and damage in the structure. That would be what we do in a typical linear elastic model. If you really want to look at nonlinear modeling, then of course there's a preload cases of effects of damage that you could use, but that's not always the most practical way to go about it.
Okay, so I will take one more, the last question, that is by Sudarshan Sesetti, who is asking, how can we access load testing for special structures like cable stayed bridge, balanced cantilever, suspension bridges, etc.? That's
as well an excellent question. And if you look at most bridge guidelines and codes, and I'm not quite sure how is the case in the Indian codes, but for example, the manual of bridge evaluation and the manual for bridge load rating through load testing, they all state these recommendations are not for long span bridges. And of course, long span bridges, they're a category in themselves. Cable stayed bridges, you have other effects to look at. So the general recommendations of really knowing what is it that you want to achieve with the load test, what's the objective of the load test, and then seeing how you're going to apply the load to the bridge and how you're going to measure the responses. Those general recommendations still hold true, but the practical application can be more difficult because it's just a more complex structure that you're dealing with.
Yeah, so I think with that, because of the time constraints, we have to close it. But I would only request you, Dr. Lansot, if we can send the balanced questions to you, and if you can leisurely reply, so that at least we can share those responses with the participants. That would be great. And another request to you, if you can also send us the handouts of your presentation, which can be shared with the participants. Some of them have requested, so that would be great. So
certainly, it would be my pleasure.
Yeah, thank you. And with this, I would like to close today's session. I must profusely thank you, Dr. Lansot, for accepting my invitation and enlightening us with this excellent presentation and enriching our knowledge. And we are, as Mr. Jagopal mentioned, we are in the process of modifying, amending our codes on the load testing. And should we require any further, your views, I would not hesitate to sort of connect with you and get your views also on the draft code. With that, I close this session. I thank all the panelists also for giving us their time and sharing their views. Thank you very much, and thanks to all participants holding on to us late in the evening. It's almost 9 o'clock in the evening, and still you are with us. About 150 people are still with us. Great. Thank you very much, and I close the session now.